In the last several videos, we have been looking at rotations and reflections. However, until now, we have only been focusing on two dimensions. How does geometric algebra describe rotations and reflections in 3 dimensions? That is what we will look at in this video. This video is a part of From Zero to Geo, a series where we formulate geometric algebra, an incredibly powerful branch of mathematics, from the ground up. Before we get into the main part of the video, I need to give a warning. The calculations in this video are much more lengthy than anything we have seen up until this point. That's just how 3D geometry is. I don't want this video to get bogged down in these calculations, and since we have already talked about how to do calculations in geometric algebra in previous videos, I'll be skimming through most of the details. Hopefully, if you have been following along with the series and doing the exercises, you shouldn't get thrown off by this. If you have to, you can pause the video during the calculations to work through them at your own pace. Anyway, let's get to the main topic of the video. Before looking into 3 dimensions, let's briefly summarize how we think of rotations and reflections in 2 dimensions. To rotate a vector u by the angle between 2 unit vectors v and w, we calculate the product u-v-w. We can think of the product vw on its own to represent the rotation, and we call such a product a rotor. 2D rotors can be written as a complex number of the form a plus bi, where I is e12, the unit bivector in the 2D plane. To rotate by a given angle, we can use a complex exponential to create a rotor that represents rotating by that angle. Finally, we can calculate reflections by using a vector sandwich. The sandwich product u-v-u represents reflecting v across the mirror given by the vector u. Finally, by combining these ideas, we saw that a double sandwich is both 2 reflections and a rotation by a double angle, so 2 reflections is a rotation. While we usually apply 2D rotors on the right of vectors, we can also apply rotors on the left of vectors by using the reverse. In 2 dimensions, multiplying a vector by a rotor on the right is the same thing as multiplying the vector by the reverse of the rotor on the left. So how do we represent these ideas in 3 dimensions? Before we look into this, try to figure it out for yourself. A word of warning, this is pretty complicated and it took a while for mathematicians to find the answer. Even if you can't figure it out yourself, playing around with these ideas should help you get better acquainted with geometric algebra. I'll give you a bit of a hint. While some of the 2D formulas don't work directly in 3 dimensions, play around with them in 3 dimensions anyway and see if you can find some way to fix the issues that arise. Please pause the video and give this your best attempt before continuing. Reflections turn out to be simpler, so let's look at them first. Given 2 vectors in 3D space, how can we reflect one across the other? Well, notice that the 2 vectors live in a 2D subspace. In that 2D subspace, we can calculate the reflection using a sandwich product. So in 3D, that same sandwich product will still calculate the reflection. Thus, in 3 dimensions, reflections are the same as in 2D. Well, not quite, since in 3D, we often want to reflect through planes instead of lines, but we'll get to that in a future video. For now, just know that like in 2D, the sandwich product of vectors reflects one vector across another. So let's now move on to 3D rotations. First of all, how can we even describe a 3D rotation? In 2D, we can describe rotations purely with an angle and one of 2 directions, clockwise or counterclockwise. In 3D, things are basically the same, but with one big difference. We have many more directions. Here are several cubes all rotating in different directions. How can we specify the direction of rotation? There are 2 ways to do this. The traditional way is to notice that whenever we rotate, there is a single line that is unchanged by the rotation. This line is called the axis of rotation. The issue with this idea is that it doesn't generalize easily to other dimensions. For example, in 2 dimensions, rotations don't have an axis line. There are ways to define axes in other dimensions, but we won't do that here. So what's the other way of describing the direction of rotation? Well, think about the bivector that is perpendicular to the axis. We can see this bivector as being the plane that the rotation is happening in. We call this plane the plane of rotation. This idea of the plane of rotation generalizes to other dimensions much more readily than axes do. For example, the plane of rotation exists in 2D, and there, it's the entire space. Because it generalizes much more nicely, we will describe rotations in terms of planes of rotation. To be explicit, to describe a rotation, we will pick a bivector in the plane of rotation and then specify an angle to rotate by. So, we could say something like rotate by 20 degrees in the plane given by E12 plus 2E13. Before going into how we calculate rotations using geometric algebra, I want to look at how exactly 3D rotations affect vectors. Consider rotating a 3D vector in the E12 plane. If we look at the components of a vector undergoing this rotation, we see that the E3 component is not changing. This is a general feature of 3D rotations. When rotating a vector, we can split the vector into two parts, one which is in the plane of rotation and the other which is perpendicular to it. Then, the rotation will affect the part that is in the plane of rotation while leaving the perpendicular part unchanged. So how do we actually calculate rotations? Your first idea might be to try to use the 2D rotation formula. Say we wanted to rotate this vector by the angle between these two other unit vectors. If we try to use the 2D rotation formula here, we end up getting a trivector component in the result. Rotating a vector should produce another vector, showing that the 2D rotation formula doesn't work in 3D. We need to try something else. The next idea we will try is to explicitly utilize the fact that rotations only affect the components of the vector that are in the plane of rotation. In this situation, this is the plane of rotation. We can find the parts of U that are parallel and perpendicular to this plane and then use the 2D rotation formula on the parallel part and leave the perpendicular part alone. Rotating the camera a bit, we see that if we add the rotated parallel part and the unrotated perpendicular part, we get the correct rotation. However, splitting the vector into parallel and perpendicular parts can be annoying, especially when the bivector is not axis aligned like it is here. Let's keep looking for a simpler way to do these calculations. Another idea is to use two reflections. In 2D, reflecting across two vectors ended up causing a rotation by 2 times the angle between the two vectors. Does this idea work in 3 dimensions? Well, we already saw that the 2D reflection formula works in 3D, so let's try it out. Well, it did produce a vector that looks like the original vector rotated by 2 times the angle from V to U, but it's hard to verify that this is actually true without looking at components. But even if we could see the components used in this case, that wouldn't prove that this process works in general. Can we prove that? Well, we know that 3D rotations can be calculated by splitting the vector into parts that are parallel and perpendicular to the plane of rotation. If we do this split in the double sandwich product, we can distribute to get 2 different terms. The parallel part is in the plane of rotation, so it rotates by 2 times the angle from V to U by the 2D argument in the last video. For the perpendicular part, the first reflection flips it completely around, and the second reflection flips it completely around again back to where it started. Thus, the perpendicular part is not affected by the double sandwich product. So we see that in 3D, the double sandwich product rotates the parallel part by 2 times the angle, while it doesn't do anything to the perpendicular part. This is precisely how we rotate vectors in 3 dimensions, showing that doing 2 reflections using the double sandwich product is a valid way to calculate 3D rotations. Personally, I don't find this process too intuitive. The fact that 2 reflections is a rotation is useful, but it's hard for me to picture it. Furthermore, this way of rotating rotates by 2 times the angle between the vectors used, which can be annoying. While this method is the best method we have found so far, let's keep searching for alternative ways to calculate this rotation. Recall that in 2 dimensions, the reason that a double sandwich caused a double rotation was that we could think of the double sandwich as being 2 instances of the 2D rotation formula. We can think of the double sandwich in 3D in the same way. Given 2 unit vectors v and u, we can calculate their product r and think of it as a rotor. Because the double sandwich worked in 3D, we can try multiplying a vector w by r on the right and by the reverse of r on the left. This, once again, produces a 3D rotation by 2 times the angle of r. In the end, This is basically just a way to rephrase the double sandwich way of rotating from earlier. I personally find it more intuitive than the double sandwich, but it still has the double angle problem since we are multiplying by r twice. It turns out that no matter what we do, this double angle thing will keep showing up. This is just how things have to be in higher dimensional geometric algebra. Whenever we try to rotate by a particular angle theta, we will end up rotating by 2 times theta. Well, if the problem is that we are rotating by 2 times theta when trying to rotate by theta, what if we instead try to rotate by theta over 2? Then, when the double angle thing kicks in, the end result will be a rotation by theta. However, until now this angle has been the angle between two vectors, which is not always easy to control. But there is a way to rotate that does allow you to use an arbitrary angle: complex exponentials. In 2D, we rotate a vector by an angle theta by multiplying the vector by e to the I theta, or on the left by e to the minus I theta. Because 3D rotations require us to apply rotors on both sides of the vector, the 3D version of these formulas is e to the minus I theta times v times e to the I theta. To rotate in an arbitrary plane given by a normalized bivector b hat, we can replace I with b hat. This will rotate the vector by 2 times theta, so to rotate by theta, we can replace theta with theta over 2. This is finally a way to calculate rotations in 3D that is not affected by the double angle problem. Let's look at an example. How do we find a 3D rotor that represents rotating in the E13 plane by 40 degrees? We need to convert this angle to radians and then calculate e to the E13 times that angle over 2. We can even pick a particular vector and calculate the rotation of this vector by the rotor. Now that we have finally figured out how 3D rotations work in general, let's describe the process in detail. First, we need to know how to convert a description of a rotation into a rotor representing that rotation. To calculate the rotor representing a rotation in the plane B by an angle theta, we just calculate e to the b theta over 2, right? Well, there's a few issues here. First, we can only use exponentials like this if b is normalized. So, whenever calculating 3D rotations, make sure the bivector is normalized first. The second issue is how exactly do we calculate a 3D bivector exponential like this? Well, once we have normalized the bivector, the calculation is exactly the same as in 2 dimensions. Euler's formula holds for any multivector that squares to -1, not just I. A normalized bivector squares to -1, so e to the b hat theta over 2 is equal to the cosine of theta over 2 plus b hat times the sine of theta over 2. This does look weird when the bivector has several components, but as long as the bivector is normalized, this equation is valid. To see what the third issue is, think about how we apply a rotor to a vector in 3D. We have to calculate the reverse of a 3D rotor. How do we do this calculation? Like in 2 dimensions, we can figure this out by looking at the product of 2 arbitrary vectors in both directions. The products are much more complicated in 3D, but we can see that just like in 2D, reversing the product ended up flipping the sign of the bivector parts. Thus, to find the reverse of a 3D rotor, all we need to do is flip the sign of the bivector parts. Anyway, here is the general way we calculate rotations. To rotate a vector v by an angle theta in the plane given by a bivector b, we first normalize b and then calculate the exponential e to the b hat theta over 2 using Euler's formula. The result will be our rotor r, and then the final rotation is r dagger vr. I should probably mention at this point that this formula is a bit different than what you will usually find in the literature. Traditionally, the rotor vector sandwich product is written rvr dagger rather than r dagger vr. Which version we use is a matter of convention, and either way works as long as you change a couple of signs in certain places. I prefer r dagger vr because of the implications this convention has on how we build rotors. With r dagger vr, the rotor representing a rotation by theta is e to the b hat theta over 2. With rvr dagger, the rotor representing a rotation by theta is e to the minus b hat theta over 2. By using r dagger vr, we avoid this minus sign. Let's now look at a more computational example. Say we want to rotate the vector 3e1 minus 2e2 plus e3 by 37 degrees in the plane given by the bivector 5e12 plus 2e23. First, we need to convert the angle to radians. Next, we need to normalize the bivector. Then our rotor r is e to the product of these two values over 2. We can then throw this rotor and our original vector into a sandwich product to get the final result. Let's do an exercise. Please calculate each of the following rotations. Having done these calculations, you may be complaining about how time-consuming they are. Do we really need to do all of this to calculate something as simple as a rotation? To be blunt, yes. In 3 dimensions and above, rotations involve a lot of computations. It turns out that in practice, we often apply rotors more than we find them, which can make things a bit simpler, but there's no getting around the fact that it's a lot of work. This is why we often leave these kinds of calculations to computers. I've been making you do these calculations so that you get better acquainted with the concepts involved, but in practice, nobody ever does these calculations manually. Now, in 2D, we call the sum of a scalar and a bivector a complex number. Is there a corresponding name in 3D? There is! In 3 dimensions, we call an arbitrary sum of a scalar and a bivector a quaternion. Some people use the letters I, J, and K to represent the 3-unit bivectors in 3D, but there's some disagreement over which bivectors each letter corresponds to, so I'll just always use E12, E13, and E23 in the future. One important way that quaternions are not like complex numbers is that their multiplication is not commutative. With complex numbers, xy is always equal to yx. But with quaternions, this is no longer true. This corresponds to a geometric fact. When doing 2D rotations, if you want to do several rotations in a row, it doesn't matter what order you do them in. But in 3D, the order does matter. If you do 2 3D rotations in a different order, you usually won't get the same result. In this video, we have been looking at 3D rotations. But do you know what's even better than 3D rotations? 4D rotations. How do they work? We'll answer this question in the next video, where the answer to the question, what is a rotation, really starts to get wacky.